Like I said, there are two types of collisions, inelastic and elastic collisions. We did the inelastic collision where only momentum was conserved. Now we're going to talk about the elastic collision. Now an example of an elastic collision, again, go back to the pool table in the student center. One pool ball comes in, strikes the other pool ball, and they continue to travel off in different directions, okay? They might be traveling along the same path, but they're traveling in different directions. Now, they did not stick together. And since they didn't stick together, that means that it is not an inelastic collision, it is an elastic collision. Now, when they interacted with each other, yes, a little bit of energy was lost. We think about the sound that was given off from the interaction. We think about the tiny little bit of friction that happened when the two interacted with each other. But for the most part, since we consider that interaction to be almost instantaneous, almost taking place over zero time, we can assume that energy is also conserved. So in an elastic collision, momentum and energy are conserved. And you'll see why this is necessary, okay? In an elastic collision, momentum and energy are conserved. I'm going to show you why this is necessary here in a second, okay? Inelastic, only momentum. Elastic, momentum and energy are conserved. So let's do an elastic example. In an elastic collision, let's have a 4 kilogram mass coming in, and that initial velocity for the first mass, V1 initial, the velocity for the first mass is 2 meters per second. Let's make it easy. Let's have a 2 kilogram mass, and its initial velocity, the velocity of the second mass initial, is equal to 0. Be careful with your notation on this, okay? Be super careful. You're going to have a lot of velocities flying around, okay? Now after they hit, they are now going to travel with different velocities. They're not stuck together. So we have the 4 kilogram mass, and it's traveling with some V1 final that we don't know. And the 2 kilogram mass is now traveling with some V2 final. And that's traveling with a velocity that we don't know, okay? Let's see what happens when we just try to do the momentum conservation. So the momentum initial, momentum final, momentum is a vector quantity. The initial momentum is all inside the 4 kilogram mass. So that's going to be 4 kilograms multiplied by its velocity, 2 meters per second. This guy had 0 momentum at the start because its initial velocity was 0, so we don't have to worry about that. And the momentum final now, here's where it gets tricky. We have the 4 kilogram mass multiplied by V1 final. Again, this is why notation is so important here, guys. V1 final with the mass, 4 kilograms. I'm saying that's the initial one, all right? Plus the 2 kilogram mass times its V2 final. Now look here. We can't solve this. We have 2 variables. So this should set off an alarm in your head saying, uh-oh, I need another equation. And that's another way that you remember that for an elastic collision, energy is also conserved. Now, if energy was also conserved, then that means that in this case, energy initial is equal to energy final. That means that the kinetic energy initial, because we're only dealing with moving objects, there was no movement up or down, the kinetic energy initial must be equal to the kinetic energy final. The kinetic energy initial, remember that energy is a scalar quantity, so I don't have to worry about directions here, which is really nice. 1/2 the 4 kilogram mass multiplied by its velocity squared, which was 2, so 2 squared. The initial energy of the second mass was 0 because it wasn't moving. And now I've got 1/2 the 4 kilograms multiplied by its V1 final squared plus 1/2 the 2 kilogram mass times V2 final squared. Again, make sure you line up the velocities with their respective masses. That's why it's really important to draw a picture at the start of this problem. Now here's where it sucks, guys, and I'm sorry about this, but I've got one equation here, and I've got one equation here. Yeah, I've got a system of equations, and in this equation, the variables are squared. This ain't pretty, This ain't nice, and this ain't fun. So yeah, you now have to solve a system of equations. You didn't really think I was just going to give you guys 3 days to watch YouTube videos and act like you're working on problems right now, right? Let's make this interesting, shall we? This is the last video I'm going to show before I get back into class, okay? So when I get back into class on Monday, for this example up here on the board, you are going to turn in on Monday a completed solution for this problem. Every one of you, individually, okay? Some of you will not finish watching these videos, and therefore you will have nothing to turn in on Monday. Now, you could warn your friends, if you're one of those good students that's watching all these videos right now, you could warn your friends and let them know that Mr. Steinman just gave them an assignment at the end of this YouTube video to give me a solution to this problem. Or maybe you don't let your friends know that. I don't know. I'm going to let you guys decide that. But I expect this problem to be completed. I've set it up for you. Now it's just solving a system of equations. I expect this problem to be completed on a separate sheet of paper, and you will turn this into me first thing Monday morning when I see you guys when I get back from my trip. Okay? Very nice. Good luck!